In the next 5 seconds, you are about to see one of the most powerful machines humans have ever built. A plant that can light up millions of homes by using energy hidden inside atoms smaller than dust. From the outside, it looks like a giant industrial city by the sea. Concrete buildings, long pipes, cooling towers, and white vapor rising into the sky make many people think of danger, ideation, and disaster. But here is the surprising truth. Inside a nuclear power plant, the thing that actually turns the turbine and makes electricity is not radiation, not lightning, and not some blue fire from a science fiction movie. It is steam. Simple steam. The same thing you see above boiling water becomes the vital link that turns nuclear energy into the electricity we use every day. But how can a small piece of fuel create enough heat to run a whole power station? And why can a tiny loss of control become so serious? To understand that, we have to move step by step into the heart of the plant. The deeper we go, the clearer it becomes that nuclear power is not simply safe or dangerous. It is a constant balance between energy, control, heat, pressure, and time. At the center of the plant is the nuclear reactor. This is the heart of the whole system. But this heart does not beat with blood. It works through a process called fission. Inside the reactor are fuel rods. These rods usually contain processed uranium. Uranium is special because its atoms can split when they are hit by tiny particles called neutrons. When a uranium atom splits, it releases a large amount of heat. It also releases more neutrons. Those new neutrons can hit more uranium atoms, and the process continues. This is called a chain reaction. When people hear the words chain reaction, many think of an atomic bomb, but a nuclear power plant is very different. In a bomb, energy is released almost all at once. In a power plant, the reaction is slowed down and controlled. It is more like keeping a fire burning at a steady level, instead of letting it explode. To control the reaction, the reactor uses control rods. These rods are made from materials that can absorb neutrons. When the plant needs less power, the rods move deeper into the reactor and absorb more neutrons. That slows the reaction. When the plant needs more power, the rods are pulled back a little, allowing more neutrons to keep the reaction going. A small movement of these rods can change the pace of the entire reactor. This is what makes nuclear power so different from coal or gas. It does not make heat by burning fuel. It makes heat by splitting atoms. A very small amount of nuclear fuel can hold a huge amount of energy. One small fuel pellet can contain as much energy as hundreds of kilograms of coal. That is why a nuclear power plant can run for a long time without needing fuel deliveries every day. But great energy always comes with great responsibility. Inside the reactor, heat rises quickly. Without cooling, the reactor core can overheat. That is why water is usually placed around the fuel rods. Water takes heat away from the core. In many reactor designs, water also helps slow down neutrons so the reaction can continue in a controlled way. In simple terms, water is both a heat carrier and part of the control system. Now look at the pipes. Hot, liquid, vapor, and flowing machinery in the video. Imagine a huge loop inside the plant. Heat from the reactor is transferred to water. The water becomes very hot. Pressure rises. In some reactor designs, the water turns into steam inside the reactor system. In other designs, the hot water passes its heat to another water loop, and that second loop becomes steam. The design can change, but the goal is the same: create high-pressure steam. That steam is the force that spins the turbine. A turbine is one of the most important parts of the plant. Think of it as a giant fan, but instead of using electricity to spin, it is pushed by powerful steam. The steam rushes through the turbine blades and makes them turn at high speed. The turbine is connected to a generator. Inside the generator, spinning motion is turned into electricity. This is the key idea. Uranium does not directly become electricity. Uranium creates heat. Heat creates steam. Steam spins the turbine. The turbine spins the generator. The generator makes electricity. It sounds long, but it happens with great precision every second. After the generator makes electricity, that electricity is not sent straight to homes. First, it passes through transformers that raise the voltage to a very high level. Why? Because high voltage allows electricity to travel long distances with less energy loss. After that, electricity moves through power lines, substations, and local grids. Finally, the voltage is reduced so it can safely power homes, hospitals, factories, and offices. Here is something many people do not notice. Nuclear power is a steady power source. It can run day and night. It does not depend on sunlight like solar power. It does not depend on wind like wind power. Once a reactor is running steadily, it can provide a large amount of power for a long time. This is why many countries see nuclear energy as part of the plan to reduce carbon emissions, especially as demand for electricity keeps growing because of electric cars, data centers, artificial intelligence, and modern industry. But the story is not only bright. Whenever we talk about nuclear power, three names often appear: 3 Mile Island, Chernobyl, and Fukushima. These accidents changed the way the world thinks about nuclear energy. Each accident had different causes, but all of them showed one lesson: cooling and control can never be taken lightly. This is an important idea. When the chain reaction stops, the reactor does not instantly become cold. The fuel still produces what is called decay heat. This heat comes from unstable materials left over after fission. It is much slower than full power heat, but it can still be dangerous if cooling is lost for too long. So nuclear safety is not only about controlling the reactor while it is running, it is also about cooling the reactor after it shuts down. That is why a modern nuclear plant does not rely on just one safety system. It has many layers of protection. The first layer is the fuel itself. The second is the metal tube around the fuel. Then come the cooling systems, the reactor vessel, and the thick concrete containment building. Modern plants also have emergency shutdown systems, emergency cooling systems, backup power, diesel generators, batteries, and passive safety features that can work even if people cannot act right away. When the video shows white clouds rising from cooling towers, many viewers may think it is toxic smoke or radiation. Most of the time, it is only water vapor. Cooling towers help cool water after steam has passed through the turbine. After steam gives its energy to the turbine, it loses pressure and must be turned back into water. That water can then return to the system and absorb heat again. This creates a repeating cycle. Plants built near the sea or a large river often use that water source for cooling, but the plant must monitor water temperature and quality, because released heat must not harm the surrounding ecosystem. A good question is this: if nuclear power is so strong, why does every country not build many nuclear plants? The answer is costly, time, rules, and public trust. A nuclear plant requires a very large investment. It can take many years to plan, and build. It also needs highly trained workers and very strict safety rules. Every action must be checked. Every process must be recorded. Every part must be inspected. There is also the issue of nuclear waste. Used nuclear fuel is still radioactive and still gives off heat. It cannot be thrown away like normal waste. Used fuel is often stored in water pools for many years, then moved into strong, dry containers. This is one of the biggest debates around nuclear energy. At the same time, it is important to be fair. Nuclear waste is small in volume compared with the smoke and carbon dioxide made by fossil fuel plants for the same amount of electricity. The problem is how carefully it must be managed, and for how long. Nuclear energy forces people to think about future generations. In recent years, the world has started talking more about new reactor designs, including small modular reactors, often called SMRs. These are smaller reactors that could be built in stages and used in places that do not need a giant power station. Some designs also focus on passive safety. using gravity and natural water flow instead of relying only on electric pumps. Beyond fission, there is an even bigger dream: fusion. Fusion joins light atoms together, the same basic process that powers the sun. It could one day offer cleaner energy, but it is still extremely hard to control. For now, fission is the nuclear technology that already produces large amounts of electricity. Back to the plant in the video. The blue light, electric effects, and huge machines may look like a scene from the future, but behind the dramatic visuals is a very simple principle: control heat. A nuclear power plant is a giant system built to do three things. First, create heat in a controlled way. Second, turn that heat into motion. Third, turn that motion into electricity. If control is strong, nuclear power can provide large amounts of low-carbon energy. If control is weak, the results can be serious. This is why nuclear power always creates debate. Supporters say the world cannot fight climate change with only weather-based energy sources, and that nuclear power gives steady, low-carbon electricity. Critics worry about accidents, waste, high cost, security risks, and long construction times. Both sides have reasons. The real answer is not to worship nuclear power or reject it completely. The first step is to understand what it really is. If we only look at disasters, we miss a technology that has powered many countries for decades. If we'd only look at benefits, we forget that this technology does not forgive carelessness. Nuclear power cannot run on hope. It needs science, discipline, transparency, independent checks, and safety systems built to handle mistakes from machines, and even nature. If we look deeper, nuclear power is also a story about trust. With solar panels, people can see sunlight. With wind turbines, people can see blades turning. But nuclear power depends on processes we cannot see. We cannot see neutrons moving through the reactor. We cannot hear uranium atoms split. Most people only see concrete buildings, cooling towers, and white vapor. Everything else depends on instruments, engineers, safety rules, and public confidence. That invisible part is what makes nuclear power feel both fascinating and frightening. We know something powerful is happening, but we cannot see it directly. When it is controlled well, it can provide clean and steady power for decades. When it is treated carelessly, it can create damage that lasts far beyond the plant itself. One important detail is that nuclear plants are designed with the idea that problems can happen. A valve can fail. A pump can stop. A sensor can give the wrong reading. An earthquake, flood, fire, or loss of outside power can test the plant. That is why there must be backup after backup. So when you see pipes, pumps, tanks, pressure valves, and cooling systems in the video, they are not just technical decoration. They are the survival network of the plant. Nuclear fuel creates heat, but the cooling system decides whether that heat stays under control. The turbine creates electricity, but the protection systems decide whether the plant can operate safely for many years. Another thing that makes nuclear power special is the time scale. A plant can take more than 10 years to plan and build. It can operate for 40, 60, or even 80 years if it is maintained well. Used fuel may need to be managed for many generations. Few technologies force people to think so far ahead. In a world that often focuses on quick results, nuclear energy reminds us that some choices reach far into the future. When we watch the plant glow at sunset, with steam rising and power lines carrying electricity away, we are not just looking at an industrial site. We are looking at an agreement between humans and nature. Nature gives us huge energy hidden inside atoms. In return, it demands knowledge, discipline, and humility. Atoms do not care about human ambition. The laws of physics do not forgive overconfidence. If we understand them and respect them, they serve us. If we ignore them, the price can be high. That may be why nuclear energy is so gripping. It is not just another power source. It is a symbol of our ability to reach deep into matter itself. Long ago, humans burned wood, Later, we burned coal, oil, and gas. We built dams, collected sunlight, and captured wind. But with nuclear power, we are not only using chemistry or natural motion, we are using energy from the structure of matter itself. That is a huge step in the history of energy. But the stronger the tool, the bigger the responsibility. Should countries build more nuclear plants to cut carbon emissions? Should they accept the high cost in return for steady long-term electricity? There is no single easy answer. Each place has different land, money, law, and public opinion. But to debate nuclear power well, we must first understand it well. Fear alone hides the potential. Excitement alone hides the risk. A fair view must hold both sides at once. Nuclear power is powerful. It produces low-carbon electricity while running. It can provide steady energy, but it's also expensive, complex, sensitive, and needs serious management. And the most amazing part is this. Everything begins with one tiny event. A neutron hits a uranium atom. The atom splits. Heat is released. Water gets hot. Steam rushes through a turbine. A generator spins. Electricity appears. From one invisible event, an entire city can light up. Imagine turning on a lamp at night, charging your phone, opening your computer, watching a video, or running a factory machine. Some of that electricity may have traveled through a chain like this. From deep inside a reactor core, through pipes, turbines, transformers, and power lines, energy finally reaches the outlet in your room. The journey is invisible, but it is one of the most complex systems humans have ever built. So is nuclear power the future? Or is it a risk? Maybe it is both. It is a future if it's managed with science, honesty, and responsibility. It is a risk if people hide mistakes, ignore safety, or chase short-term gain. Technology is not good or bad by itself. The outcome depends on how humans design it, operate it, and watch over it. In the 21st century, demand for electricity is rising fast. At the same time, the world needs to reduce carbon emissions. That is why nuclear power has returned to the center of the energy debate. Some countries are closing reactors, others are building new ones. Some are betting on small reactors, others are researching fusion. But the need for electricity is not going away. Hospitals need it, data centers need it, factories need it, daily life needs it. The future may not depend on one energy source alone. It may be a mix of solar, wind, hydro, storage, energy saving, and nuclear power where it makes sense. Whatever the choice, the most important thing is to understand the benefits, the costs, and the risks. Behind those white clouds rising into the sky is not just a power plant. It is a story about human ambition, the desire to take energy from the heart of the atom, control something once seen as